Somewhere beneath every application you open and every file you touch, a quiet layer of logic does the work of keeping your computer alive. It organizes memory, manages hardware, schedules programs, and preserves order in a world built from millions of electrical signals. This hidden foundation is the operating system, a system designed to make everything else possible. Tonight we explore it slowly, one concept at a time, drifting through calm explanations of how computers manage themselves. Chapter 1: The Purpose and Evolution of Operating Systems. Operating systems sit at the center of modern computing. They provide structure, consistency, and usability for machines that would otherwise be difficult to control. Without an operating system, a computer becomes a collection of components waiting for instructions. The operating system coordinates these components, presenting a unified environment where programs run, hardware interacts, and users work. This chapter begins by examining the history, purpose, and gradual evolution of operating systems as they adapted to new technologies and changing needs. In the earliest computers, no operating systems existed. Programmers interacted directly with hardware, using switches, punched paper, or handwritten machine code to control behavior. Each program required detailed knowledge of the system's internal workings. Because early machines executed one task at a time, programmers had to manage every detail manually, from memory allocation to device control. This approach worked for small research systems, but became impractical as machines grew more powerful and workloads expanded. The need for a structured intermediary between humans and hardware became clear. The first operating systems emerged in the 1950s and 1960s. These early systems automated simple tasks such as loading programs, managing basic I/O, and switching between jobs. Batch processing represented one of the earliest forms of automation. Instead of requiring operators to load programs manually, batch systems queued jobs and executed them sequentially. This reduced idle time and allowed machines to run continuously. Although users could not interact with programs while they ran, batch processing improved efficiency and introduced the idea of centralized management. Time-sharing systems arrived in the 1960s and 1970s, transforming the role of operating systems. Instead of dedicating a machine to one job at a time, time-sharing allowed multiple users to interact with the computer simultaneously. The operating system divided processor time into small slices, giving each user the illusion of continuous access. This innovation supported interactive computing, enabling research labs, universities, and corporations to use computers for communication, development, and experimentation. The concepts of user accounts, permissions, and resource isolation began to appear during this era. As hardware evolved, operating systems expanded their capabilities. The shift from centralized mainframes to personal computers in the 1980s brought operating systems directly into everyday life. Systems such as MS-DOS, early Windows versions, Mac OS, and Unix variants introduced graphical interfaces, improved file systems, and expanded application support. Users interacted with icons, menus, and windows instead of command lines. Operating systems adapted to new input devices, storage technologies, and network capabilities. Each advancement reshaped how people used computers, making them more accessible and versatile. The rise of networking influenced operating system design significantly. As computers connected through local networks and eventually the Internet, operating systems integrated networking stacks to handle communication, routing, and sharing. File sharing, remote access, and distributed applications depended on reliable networking support. Security also gained importance as systems became accessible from outside sources. Operating systems enforced authentication, controlled permissions, and protected system resources against unauthorized access. Virtualization introduced another major shift. Instead of relying on one system per machine, virtualization allowed multiple operating systems to run on a single physical host. Hypervisors managed hardware access, while each virtual machine operated independently. This approach improved resource efficiency, simplified testing, and enabled cloud computing. Operating systems adapted by supporting virtual environments, para-virtualized drivers, and advanced resource scheduling techniques. The distinction between physical and virtual systems blurred as virtualization became standard practice in enterprise environments. Mobile operating systems added yet another dimension. Systems such as iOS and Android, designed for smartphones and tablets, introduced touch interfaces, application sandboxes, and energy-efficient scheduling. These systems optimized performance for mobility, battery conservation, and sensor integration. They brought operating system concepts into the hands of billions, shaping modern computing habits and expectations. Today's operating systems form complex, layered ecosystems. They support multitasking, memory protection, process isolation, device abstraction, and sophisticated scheduling. They integrate with cloud services, authentication providers, and distributed applications. Some operating systems specialize in servers, others focus on consumer devices, embedded systems, or high-performance computing. Despite these differences, all operating systems share common principles. They manage resources, provide interfaces, ensure stability, and create predictable environments for running programs. The evolution of operating systems reflects a broader narrative in computing: the continuous move toward abstraction, efficiency, and user accessibility. Early systems required explicit, low-level control. Modern systems handle millions of operations silently, allowing users to focus on tasks rather than machinery. Each generation brought new challenges, from managing shared resources to supporting global networks. The result is an essential layer of computing that balances hardware complexity with human expectations. This chapter provides the historical and conceptual foundation for everything that follows. Later chapters will explore internal components of operating systems, including processes, memory, file systems, scheduling, and security. For now, the evolution of operating systems shows how these systems grew from simple job managers into the sophisticated platforms that support modern computing. Chapter 2: Windows, Unix, Linux, and Mac OS. The four major operating systems. Families, modern operating systems took shape when personal computers reached global availability in the late 1980s and early 1990s. During this period, four major families emerged and began shaping the way people interacted with technology. These families were Windows, Unix, Linux, and Mac OS. Each developed from unique goals and philosophies. Each took a different approach to design, usability, and system management. Today, these four families continue to influence nearly every device in use, from personal laptops to large servers in data centers. This chapter introduces their origins, architectural foundations, and the roles they occupy in modern computing. Windows began as a graphical interface built on top of MS-DOS. Early versions provided simple window management, limited multitasking, and basic device support. As hardware became more powerful, Microsoft moved toward a full operating system with its own kernel and unified architecture. Windows NT marked a turning point. It introduced protected memory, preemptive multitasking, and structured security controls. These foundations carried into later consumer versions. Over time, Windows became the dominant desktop platform, supported by a large software ecosystem and broad hardware compatibility. Enterprises adopted Windows because it integrated well with corporate networks, identity systems, and administrative tools. Unix followed a different path. Developed in academic and research environments, Unix focused on simplicity, portability, and text-driven interfaces. Its design emphasized small tools that performed single tasks well. These tools could be combined to create powerful workflows. Unix systems relied heavily on clear file system structures, process separation, and well-organized permissions. Because Unix was written in the C programming language, it could be adapted to many hardware platforms. This allowed Unix to spread through universities, scientific institutions, and early commercial environments. Its influence shaped many later systems, including Linux and Mac OS. Linux emerged in the early 1990s as a free and open-source Unix-like system created by volunteers. Its kernel offered flexibility, transparency, and community-driven development. Anyone could study its code, improve it, or build custom versions. Linux grew rapidly and became widely used for servers, cloud environments, embedded systems, and development platforms. Its modular structure allowed organizations to select only the components they needed. Distributions such as Red Hat, Ubuntu, Debian, and many others provided organized collections of tools, installers, and support. Linux became essential for web servers, container platforms, and large-scale computing because it offered stability, performance, and deep customization. Mac OS developed from the Unix family but took a distinct direction. Apple built Mac OS with Unix-based underpinnings combined with a strong graphical interface. This combination produced a system that provided both stability and user-friendly design. Mac OS standardized much of its environment, limiting fragmentation and ensuring consistent behavior across devices. The system integrated closely with Apple hardware, which allowed tight control of performance, power management, and security. Over time, Mac OS became a preferred platform for creators, researchers, and developers who valued its predictable environment and Unix-based tools. Although these four families share common principles, they differ in architecture and philosophy. Windows uses a hybrid kernel design that blends elements of microkernel and monolithic structures. It includes a wide range of subsystems for compatibility and supports an extensive variety of drivers. Unix and Linux follow more traditional monolithic kernel designs where core functions remain integrated but modular. macOS uses a layered approach that combines a Mac-based kernel with BSD components. Each system implements its own scheduling algorithms, memory structures, and hardware abstraction techniques. These differences influence performance, flexibility, and design priorities. File systems present another point of distinction. Windows traditionally used FAT and NTFS. NTFS introduced journaling, permissions, encryption support, and reliability improvements. Linux supports many file systems, including ext4, XFS, BTRFs, and others. This variety allows users to select file systems suited to performance, reliability, or advanced features. Unix systems use file systems such as UFS or ZFS. Mac OS uses APFS, which provides strong snapshot capabilities, encryption, and efficiency for solid-state drives. File system design influences speed, data safety, and long-term maintenance. Security models also differ. Windows uses access control lists, group policies, and centralized management through directory services. Unix and Linux rely on permission bits, ownership structures, and extended permissions such as SE-Linux or AppArmor. Mac OS combines Unix-style permissions with additional integrity protections enforced at the system level. Each security model reflects the environment in which the system evolved. Windows emphasizes enterprise-level control. Unix focuses on clear separation of users and processes. Linux emphasizes flexibility and administrative control. macOS emphasizes system integrity and user privacy. Use cases help explain why these systems coexist. Windows dominates the desktop market because of application availability and familiarity. Enterprises use Windows for office environments, administrative tasks, and domain-based identity systems. Linux dominates servers, cloud platforms, and research environments because of stability, scalability, and open-source development. Unix remains important in specialized sectors such as telecommunications, scientific computing, and high-reliability environments. macOS supports creators, developers, and users who value a stable, curated, and cohesive ecosystem. Interoperability also plays a role in modern computing. Windows now includes compatibility layers that support Linux tools. Linux integrates with cloud platforms used by organizations that also run Windows-based identity systems. macOS includes native Unix utilities and supports cross-platform development. These systems no longer exist in isolation. They share protocols, development frameworks, and standards that allow them to operate together across networks, containers, virtual machines, and cloud environments. Despite differences in design, all four families share common goals. They must manage hardware, schedule processes, support memory structures, handle files, and ensure security. They must integrate with networks, run applications, and support users. They adapt to new technologies such as virtualization, cloud computing, distributed systems, and mobile platforms. They evolve as hardware changes, software expands, and user expectations rise. Understanding these four families provides a foundation for exploring the deeper mechanisms of operating systems. Later chapters will examine processes, memory management, file systems, scheduling, and system calls. Each of these topics appears across all four families, but each system implements them in unique ways. By learning their histories and design philosophies, readers can appreciate how operating systems shape modern computing. Chapter 3: Processes, Programs, and How the Operating System Manages. Operating systems exist to run programs, and the way they manage these programs forms one of their most important responsibilities. A program is a set of instructions stored on disk. A process is what that program becomes when it is loaded into memory and executed. This distinction matters because the operating system does not interact with programs directly. It interacts with processes, which are active entities that use processor time, memory, files, and system resources. This chapter explores how operating systems create processes, manage them, supervise their behavior, and coordinate their actions. When a user opens an application, the operating system begins by loading the program into main memory. It allocates space for the code, data, stack, and other structures the program needs to function. The operating system then creates a process control block. This block stores essential information such as the program counter, register values, memory layout, and resource permissions. The process control block allows the operating system to pause, resume, or terminate the process at any time. It acts as a record of the process state, making scheduling and management possible. Processes transition through several states while they run. These states include new, ready, running, waiting, and terminated. A process enters the new state when it is first created. It enters the ready state when it is prepared to run but is waiting for processor time. It enters the running state when the scheduler assigns it to the processor. It enters the waiting state when it must pause for input or another event. It enters the terminated state when it completes execution or is stopped by the operating system. Moving between these states allows the operating system to control many processes at once, even though only one can run on a single processor core at a given moment. Context switching allows the operating system to shift the processor from one process to another. During a context switch, the system stores the current process state in its process control block. It then loads the state of another process and prepares it to run. This happens quickly, often many times each second. The result is the illusion of parallel execution, even on a processor with a single core. Modern systems with multiple cores truly run several processes at the same time, but context switching remains essential for balancing workloads. Processes may create other processes. The creating process becomes a parent and the new one becomes a child. Together they form a process tree. Some operating systems allow parents to wait for children to complete. Others track resources used by children and reclaim them when they finish. This structure helps organize system activity. It also enforces security boundaries. For example, a user can start multiple applications, but each runs in its own process with its own permissions. Processes need access to files, memory segments, and communication channels. The operating system enforces rules about which resources a process may use. These rules help protect the system. A process should not read another process memory. It should not modify another process files. It should not control hardware without permission. The operating system maintains these boundaries by assigning identifiers, controlling access tables, and monitoring process requests. These measures ensure safety and prevent accidental or malicious interference. Inter-process communication allows processes to exchange data. Communication methods include pipes, message queues, shared memory, and sockets. Pipes allow linear communication between sender and receiver. Message queues permit structured exchanges where data is stored until read. Shared memory offers fast communication by allowing processes to work inside a common memory region. Sockets support communication across networks, allowing processes on different machines to interact. Each method requires careful control by the operating system to prevent corruption or unauthorized access. Processes may compete for resources. They may need the same files, devices, or memory segments. Without proper management, competition could cause deadlock, where two or more processes wait indefinitely. The operating system monitors requests, allocates resources fairly, and resolves conflicts. Some systems use ordering rules. Others apply avoidance strategies that prevent dangerous combinations of resource requests. Resource management ensures smooth operation and prevents processes from blocking one another permanently. Modern operating systems also support process isolation. Isolation protects the system by preventing one process from affecting another. It confines faults to individual processes, preventing failures from spreading. Isolation relies on protected memory, controlled system calls, and well-defined permissions. Virtual machines and containers extend isolation further by creating environments that behave like independent systems. These technologies rely on process management principles, but apply them on larger scales. Processes are not always independent. Some work together to perform larger tasks. For example, a web browser may use one process to manage the interface, another to handle network requests, and others to isolate tabs. This increases stability. If one tab crashes, the entire browser does not fail. The operating system supports multi-process applications by providing communication channels and by scheduling processes so they run smoothly together. Background processes also play an important role. These processes perform tasks without direct user interaction. They handle indexing, network management, updates, printing, and security monitoring. The operating system manages these background processes just like any other. It ensures they do not consume excessive resources, interfere with active applications, or compromise system stability. Process termination occurs when a program finishes its task or when the operating system stops it. Termination releases memory, closes files, and removes the process control block. Proper termination keeps the system stable and prevents resource leaks. If processes do not release memory or file handles correctly, the operating system must reclaim them. Memory leaks and orphaned processes can slow the system or cause instability, so operating systems include mechanisms for cleanup. Understanding processes reveals how operating systems keep systems active and organized. Processes form the core of application execution, resource management, scheduling, and system stability. They allow multiple programs to run, cooperate, and communicate. Later chapters will build on these concepts by examining threads, concurrency, memory management, and scheduling. These subjects extend process management and show how operating systems coordinate many activities at once. Chapter 4: Threads, Concurrency, and Coordination. Inside the CPU, processes form the foundation of execution, but modern operating systems rarely stop at assigning one flow of work to each process. Instead, they divide work into smaller units called threads. Threads represent paths of execution inside a process. A process may contain one thread or many. Each thread runs independently, yet all threads inside the same process share memory, files, and resources. Understanding threads helps explain how operating systems handle multiple tasks, coordinate CPU activity, and support responsive applications. A thread carries its own program counter, register values, and stack. These components allow it to run as if it were an independent program, even though it belongs to a larger process. When the operating system schedules a thread, it loads the thread state and begins executing instructions. When the thread pauses, the operating system saves the state so another thread may run. Switching between threads happens quickly, giving each one a small window of processor time. This creates the appearance of parallel activity, even on a single core. Threads improve performance by allowing tasks to run without blocking each other. For example, a program that waits for input or network communication can place the waiting work in one thread while keeping another thread active. This allows applications to remain responsive. In graphical applications, one thread may manage the interface while others handle computation. In server environments, threads allow many requests to be processed at once. By dividing tasks into smaller components, systems work more efficiently. On systems with multiple cores, threads allow true parallel execution. Each core can run one thread at a time, so multiple threads can progress simultaneously. Modern processors include features such as simultaneous multithreading, where a single core can run parts of two threads at once. This increases CPU utilization and improves throughput. Operating systems include sophisticated schedulers that decide which threads run on which cores. These decisions consider fairness, priority, and efficiency. Concurrency introduces challenges. Because threads share memory, they may attempt to read or write the same data at the same time. Without protection, these actions can produce unpredictable results. This problem is called a race condition. A race condition occurs when the outcome of an operation depends on the precise timing of thread execution. Such errors can be difficult to reproduce and diagnose. Operating systems and programming languages provide tools to coordinate threads and prevent these issues. Synchronization mechanisms help threads cooperate safely. One common tool is the mutex, which stands for mutual exclusion. A mutex allows only one thread to access a shared resource at a time. When a thread locks a mutex, other threads must wait until it releases the lock. Semaphores provide more flexible control by allowing a limited number of threads to access a resource. Condition variables let threads wait for specific events. Together, these tools prevent corruption and organize thread interactions. Thread coordination must be designed carefully to avoid deadlock. Deadlock occurs when two or more threads wait indefinitely for resources held by each other. For example, if one thread locks resource A and waits for resource B, and another thread locks resource B and waits for resource A, neither can continue. Deadlock stalls progress and wastes CPU time. Operating systems and developers use ordering rules, avoidance algorithms, and careful design to prevent deadlock. Some systems include deadlock detection methods, but resolving deadlock often requires restarting one or more threads. Another concern is starvation. Starvation occurs when some threads never receive CPU time or access to resources because other threads dominate the system. Scheduling policies help prevent starvation by assigning time fairly. Priority levels allow operating systems to give important threads more time without blocking less important ones entirely. Balancing fairness and responsiveness remains an important design goal. Modern operating systems treat threads as first-class citizens. They provide thread libraries, kernel-level management, and system calls that allow programs to create, join, pause, and interact with threads. Kernel-level threads are visible to the operating system scheduler and can run on any available core. User-level threads exist inside a process and rely on the process to manage scheduling. Some systems combine both approaches. Kernel-level threads provide flexibility and performance on multi-core systems. User-level threads allow fast switching without kernel involvement. As applications grow more complex, thread design becomes increasingly important. Servers use thread pools to manage large numbers of requests efficiently. Databases use threads to handle queries, transactions, and background tasks. Operating systems themselves use many threads internally to manage memory, handle interrupts, perform housekeeping, and respond to events. Proper thread management ensures stability and performance. Concurrency also appears in asynchronous programming models. Instead of creating many threads, asynchronous models allow programs to wait for events without blocking. When an event completes, a callback or continuation runs. This approach reduces overhead by minimizing thread switching. Asynchronous programming suits workloads such as network communication, file operations, and high-volume service requests. Many modern operating systems and frameworks support both threaded and asynchronous models, allowing developers to choose the best approach. Interrupts further complicate concurrency. Interrupts occur when hardware signals the processor to handle an event. The operating system must pause the current thread, run an interrupt handler, and then resume normal activity. Interrupts support keyboard input, network packets, timers, and hardware interactions. Because interrupts occur unpredictably, operating systems must ensure that interrupt handling does not disrupt thread coordination or corrupt shared data. Process and thread scheduling work together. The scheduler decides which thread runs and when. It considers priorities, time slices, workload distribution, and fairness. Scheduling policies influence responsiveness, efficiency, and power consumption. For example, mobile operating systems schedule threads to maximize battery life. Server operating systems schedule threads to handle heavy workloads efficiently. Desktop systems aim for responsiveness so user interactions feel smooth. Threads form the foundation of modern computing concurrency. They allow programs to divide work, improve responsiveness, and utilize multi-core processors. They also introduce challenges that require careful coordination, synchronization, and scheduling. Understanding threads prepares readers for deeper exploration of memory management, file systems, scheduling algorithms, and other internal components of operating systems that rely on safe and efficient concurrency. Chapter 5: Memory Management and How Systems Organize. Information memory is one of the most carefully managed resources inside any operating system. Programs need memory to store instructions, data, variables, stacks, and temporary information. The operating system must allocate memory, protect it, share it, and reclaim it when programs complete their work. Memory management determines stability, performance, security, and efficiency. This chapter explores how operating systems organize memory, track usage, and make decisions about how to distribute this essential resource. Every program begins with a memory layout prepared by the operating system. This layout typically includes several regions. The text region contains the program instructions that remain unchanged during execution. The data region contains global variables and static values. The heap region supports dynamic memory allocation, allowing programs to request space while running. The stack region grows and shrinks as functions are called and return. These regions together form the process address space. The operating system maps each region to physical memory through a structure called a page table. To keep memory organized, modern operating systems use a concept called logical addressing. Programs do not see the actual physical addresses on the hardware. Instead, they work with virtual addresses. The memory management unit on the processor translates virtual addresses into physical ones. This separation allows the operating system to move data, reorganize memory, and protect regions without disturbing the program. Logical addressing prevents programs from interfering with one another and creates a uniform view of memory. The operating system must track which parts of memory are in use. It maintains data structures that record allocated segments, free regions, and reserved areas. When a program requests memory through system calls or language features, the operating system finds an available block and assigns it. When the program releases memory, the operating system marks the block as free. If memory is fragmented, meaning free regions are scattered, the operating system may need strategies to combine or reorganize space. Some systems use compaction techniques. Others use allocation algorithms that limit fragmentation. Protection is a crucial part of memory management. A process should not access memory that belongs to another process. The memory management unit enforces protection by using access permission bits on each page. Pages may be marked as read-only, read-write, or executable. If a process attempts an operation that violates permissions, the operating system intervenes. This prevents accidental corruption of data and protects system stability. Protection also helps contain malicious activity, since damaging actions require access to restricted memory regions. Sharing memory across processes can improve performance. Some pages contain instructions or data that multiple processes need, such as libraries or read-only resources. Rather than create separate copies, the operating system maps shared pages into multiple process address spaces. This saves memory and improves efficiency. Shared memory also supports communication when processes intentionally exchange data. However, it requires careful synchronization to prevent corruption. Memory allocation strategies vary. One common approach is fixed partitioning, where memory is divided into regions of predetermined sizes. Another approach is variable partitioning, where regions grow or shrink based on program needs. More advanced systems use paging, which divides memory into small blocks of equal size called pages. Paging simplifies allocation by avoiding external fragmentation. It also works closely with virtual memory, which appears in the next chapter. Swapping is another memory management tool. When memory becomes full, the operating system may temporarily move inactive pages or entire processes to disk. This frees space for active processes. When the swapped process becomes active again, its data returns to main memory. Swapping increases available memory but slows performance because disk operations take more time than memory access. Modern systems combine swapping with virtual memory to create efficient, flexible strategies. Memory leaks occur when a program allocates memory but never releases it. Over time, the leak consumes more and more memory, reducing available space for other processes. The operating system can detect some leaks through monitoring tools, but preventing them requires careful programming. Memory leaks reduce performance and can cause instability. Operating systems include diagnostic features that help developers find and correct leaks. Some programming languages use garbage collection to manage memory automatically. Garbage collectors examine the heap and free memory that is no longer referenced. This reduces the risk of leaks but introduces pauses and overhead. The operating system cooperates with garbage collectors by providing information about memory pages and by supporting efficient allocation mechanisms. Caching plays an important role in memory management. Operating systems use caches to store frequently accessed data from storage devices or network sources. When a program requests information, the system checks the cache before reading from slower storage. This speeds up performance and reduces load. Cache management requires balance because cached data consumes memory that could be used by programs. The operating system uses strategies to determine which items to keep and which to remove. Another important concept is memory overcommitment. Some systems allow programs to request more memory than is physically available. The operating system relies on the expectation that programs will not use all requested memory at the same time. Overcommitment increases flexibility but carries risks. If too many programs use memory intensely at once, the system may run out of space. To manage this, operating systems use policies that limit allocation or trigger protective responses. Memory management adapts to advances in hardware. Systems must support different types of memory, including traditional dynamic memory, high bandwidth memory, and non-volatile memory. They must optimize access patterns to reduce latency and improve throughput. They must handle larger address spaces as processors evolve. These changes influence paging, caching, allocation, and protection strategies. Understanding memory management provides a foundation for further study. The next chapter covers virtual memory, which expands memory capacity and improves flexibility. Later chapters explore file systems, input and output, scheduling, and resource allocation. Each topic connects to memory management because memory underpins every operation inside an operating system. Chapter 6: Virtual Memory, Paging, and Efficient Use of Physical RAM. Virtual memory allows operating systems to run programs even when physical memory is limited. It creates the illusion of a large continuous address space by combining main memory with storage on disk. This approach provides flexibility, protection, and efficient allocation. It also simplifies programming because developers do not need to manage physical memory directly. This chapter explores how virtual memory works, how paging supports it, and how operating systems use these techniques to keep systems stable and responsive. Virtual memory extends the address space available to each process. Instead of mapping every virtual address directly to a physical location, the operating system stores some data in main memory and some on storage devices. When a program accesses an address that is not currently in memory, the operating system moves the required data from storage into memory. This event is called a page fault. Page faults allow systems to load data only when it is needed. This makes efficient use of memory by avoiding the need to keep all data active at once. Paging divides memory into small blocks called pages. Pages have fixed size, usually measured in kilobytes. Virtual memory consists of virtual pages, and physical memory consists of physical frames. The operating system maintains a page table to map virtual pages to physical frames. When a program uses an address, the memory management unit consults the page table. If the page is present in physical memory, the program continues. If not, a page fault triggers data retrieval from storage. Paging supports isolation between processes. Each process has its own page table, so virtual addresses do not overlap. This prevents one process from reading or writing another process memory. It also supports shared memory by allowing multiple page tables to reference the same physical frame. Paging forms the foundation of modern memory protection and allows operating systems to enforce strict control over memory usage. Demand paging is a technique where pages load only when accessed. This reduces startup time for programs and decreases memory usage. Many programs do not use all their data during execution. Demand paging keeps memory available for other processes. However, too many page faults can slow the system. The operating system must balance memory usage and performance by controlling which pages remain in memory. Page replacement algorithms help decide which pages to remove when memory becomes full. One common strategy is least recently used, where the system removes the page that has not been accessed for the longest time. Another strategy is first in, first out, where the oldest page is removed first. Some systems use algorithms that approximate least recently used behavior while reducing overhead. Effective page replacement improves performance by keeping frequently accessed data in memory. Thrashing occurs when the system spends more time handling page faults than executing programs. Thrashing happens when memory is too full or when too many processes compete for space. To prevent thrashing, operating systems monitor page fault frequency. If faults occur too often, the system may reduce the number of active processes or limit memory allocation. Thrashing slows performance and increases wear on storage devices. Avoiding it is essential for stable operation. Swapping complements paging by allowing entire processes to move between memory and storage. When the system becomes overloaded, swapping frees memory by moving inactive processes to disk. When those processes need to run again, they return to memory. Swapping increases available memory but adds delay because disk access is slower than memory access. Systems balance paging and swapping to maintain responsiveness. Memory-mapped files provide another use of virtual memory. Instead of reading and writing files through system calls, the operating system maps the file into memory. Programs then access the file through normal memory operations. This simplifies programming and can improve performance. Memory-mapped files rely on paging to load file segments when needed. They also support shared memory for communication between processes. Large address spaces require efficient handling. Modern processors support expanded address widths, allowing systems to manage more memory than before. Operating systems must adapt page table designs to handle these large spaces. Some systems use multi-level page tables, where page tables reference other page tables. This reduces memory consumption by allocating page table entries only when needed. Multi-level structures allow flexible mapping and reduce overhead. Hardware features influence virtual memory behavior. Many processors include translation look-aside buffers, which store recent address translations. The translation look-aside buffer speeds up memory access by avoiding repeated page table lookups. When entries change, the operating system must update the translation look-aside buffer. Some systems use advanced hardware support to improve virtual memory performance. File systems interact with virtual memory. When paging loads data from storage, it relies on file system structures to locate information. The speed of the storage device affects paging performance. Solid-state drives offer faster access than traditional disks, reducing delays. Some operating systems optimize paging for different storage technologies by adjusting prefetching behavior and caching strategies. Virtual memory supports security by isolating processes. Pages have permission bits that determine whether they can be read, written, or executed. Executable code resides in pages marked as executable. Data resides in pages marked for read or write operations. These controls prevent code injection and protect against corruption. Virtual memory also supports techniques such as address space layout randomization, which makes it difficult for attackers to predict memory locations. This reduces the risk of targeted exploits. Virtual memory supports flexible allocation. Programs can request more memory than they immediately use. The operating system allocates space in the virtual address space, but delays assigning physical memory until needed. This strategy is called lazy allocation. Lazy allocation increases efficiency by avoiding unnecessary memory assignments. It also supports memory overcommitment, where programs together request more virtual memory than the system can physically provide. Overcommitment increases flexibility but requires careful monitoring. Understanding virtual memory helps explain how operating systems keep systems running smoothly even under heavy workloads. It supports flexibility, isolation, protection, and efficient use of physical memory. It adapts to hardware changes, supports advanced security features, and underpins many system-level operations. Virtual memory forms the foundation for later chapters that cover file systems, input and output, scheduling, and system calls. Each of these topics relies on memory management strategies made possible by virtual memory. Chapter 7: File Systems and How Data is Stored and Retrieved. Every operating system relies on a file system to organize information. File systems determine how data is named, stored, located, protected, and retrieved. They provide structure, reliability, and a consistent interface for applications. Without a file system, data would remain a collection of raw bytes scattered across a storage device. File systems transform those bytes into meaningful files and folders that users and programs can understand. This chapter explains how operating systems design file systems, manage storage devices, and ensure that data remains safe and accessible. A file is a collection of related data stored under a name. Files can contain text, images, programs, or any other form of information. A directory is a container that holds files and other directories. Together, they form a hierarchical structure that resembles a tree. This structure helps users navigate storage with paths that lead from the root directory to specific locations. Each file and directory has attributes such as size, timestamps, permissions, and ownership. The operating system uses these attributes to manage, access, and maintain organization. When a file is saved, the file system must decide where to place the data on the storage device. Storage devices are divided into blocks of fixed size. The file system assigns one or more blocks to hold the file data. It also stores metadata, which describes how the blocks relate to the file name and directory entry. Metadata includes information such as block addresses, file length, and modification time. The file system must update metadata carefully to avoid corruption. Fragmentation occurs when a file is stored in non-contiguous blocks. Fragmentation increases as files grow, shrink, or change frequently. Reading fragmented files takes more time because the system must access multiple locations on the device. Some file systems include tools to reorganize blocks and reduce fragmentation. Solid-state drives are less affected by fragmentation due to their fast random access, but file systems still aim to group related data together to improve efficiency. Different operating systems use different file systems. Windows commonly uses NTFS, which supports journaling, permissions, encryption, compression, and large volumes. Journaling improves reliability by recording changes before applying them. If a power loss occurs, the system can review the journal and restore consistency. Linux supports several file systems, including ext4, and btrfs. These systems offer robustness, scalability, and advanced features such as snapshots and checksums. Mac OS uses APFS, which optimizes storage for solid-state drives, supports cloning, encryption, and strong reliability features. Each file system reflects the design goals of its operating system. The file system interacts with the storage medium. Magnetic disks store data on spinning platters. Reading these disks involves moving a mechanical arm to specific tracks, which takes time. Solid-state drives store data electronically and eliminate movement, allowing faster access. The operating system uses different optimization strategies depending on the storage type. For example, solid-state drives require wear leveling to prevent damage from repeated writes to the same blocks. The file system cooperates with the device to distribute writes evenly. Reliability is essential for file systems. Data loss can cause significant harm. File systems implement protections such as journaling, checksums, and redundancy. Journaling tracks changes to metadata. Checksums detect corruption by verifying data integrity. Redundant storage techniques create multiple copies of data or use parity information to reconstruct missing blocks. Some file systems include snapshot capabilities that allow the system to preserve previous versions of files. Snapshots help recover from accidental deletions or corruptions. Permissions protect files from unauthorized access. Operating systems assign ownership to each file and directory. Owners control read, write, and execute permissions. Group permissions allow shared access for related users. Extended controls provide more granular protection. Linux and Unix rely on user, group, and other permission bits. Windows uses access control lists that specify detailed rules for individuals and groups. Mac OS combines Unix permissions with additional integrity protections. These permission systems safeguard data and maintain privacy. File paths help locate information. Absolute paths begin at the root directory and specify the full route to a file. Relative paths begin at the current directory and evaluate locations based on context. File systems support symbolic links or shortcuts that point to other files or directories. These links help organize complex structures without duplicating data. They also support flexibility in reorganizing directories without breaking references. Reading and writing files involve multiple steps. When a program requests a file, the operating system checks permissions and locates the file metadata. It then reads the block addresses and fetches the data. Writing involves allocating blocks, updating metadata, and ensuring consistency. To improve performance, file systems use caching. Frequently accessed blocks remain in memory, reducing the need to access storage repeatedly. Cache management requires careful balance to preserve data integrity. Some file systems support journaling only for metadata. Others journal both metadata and data. Full journaling offers stronger protection at the cost of performance. Write ordering rules also affect reliability. The file system must ensure that metadata updates do not occur before the associated data is stored. Otherwise, the system may reference blocks that contain incomplete or corrupted data. Journaling helps maintain correct order by controlling commit sequences. Distributed storage complicates file system design. In network-based environments, files may reside on remote machines. The operating system uses network file systems that allow local applications to access remote data as if it were stored locally. Protocols such as NFS and SMB handle requests and responses. These systems must ensure consistency when multiple users access the same files. They also must manage latency and network reliability. File systems adapt to new hardware and usage patterns. Large-scale storage environments use cluster file systems that span multiple servers and devices. Mobile devices use file systems optimized for flash storage and low-power operation. Cloud platforms use object-based storage rather than block-based storage. In object storage, files are represented as objects with metadata rather than blocks. This model simplifies scaling and distribution across many systems. Understanding file systems explains how operating systems preserve data and provide access to it. File systems manage naming, organization, protection, and reliability. Later chapters will explore input and output systems, scheduling, system calls, and security. Each of these topics depends on file systems to maintain structure and ensure dependable operation. Chapter 8: Input and Output. Systems and how devices communicate. Input and output systems allow computers to interact with the outside world. Every keystroke, network packet, file request, and display update passes through input and output pathways. These pathways must translate signals, manage timing, coordinate hardware, and deliver data to the correct destination. Input and output systems shape the responsiveness, reliability, and usability of modern computing. This chapter explains how operating systems handle devices, transfer data, and maintain efficient communication. Input devices send information into the system. These devices include keyboards, mice, touchscreens, microphones, cameras, and sensors. Output devices present information from the system to the user. These include monitors, printers, speakers, and projectors. Many devices function as both input and output, such as network cards and storage drives. The operating system must support all of these devices, even though each uses different signals and protocols. Device drivers act as translators between hardware and the operating system. Without drivers, the operating system would not know how to communicate with devices. Drivers contain code specific to each piece of hardware. When the operating system sends a request, the driver formats it into the commands that the hardware understands. When hardware sends signals, the driver converts them into formats that the operating system can process. Drivers load into the kernel or operate in user mode depending on the system design. The operating system groups devices into categories. Character devices handle data streams such as keyboards and serial ports. Block devices handle data in fixed size. Chunks such as storage drives. Network devices transmit and receive packets. Each category uses its own communication methods, buffering strategies, and scheduling rules. Managing these categories requires consistent interfaces, so applications do not need to understand the details of each device. Buffering is essential for input and output. A buffer is a temporary storage area that holds data before it moves to its final location. Buffers smooth out differences in speed between devices. For example, a keyboard sends data much more slowly than a processor can handle it. A buffer allows the processor to read several characters at once. Storage devices often use large buffers to collect or deliver data in blocks. Buffering reduces waiting time and improves performance. Interrupts support efficient communication. When a device needs attention, it sends an interrupt signal to the processor. The processor pauses its current thread, runs an interrupt handler, and then returns to normal execution. Interrupts allow devices to communicate only when necessary, rather than requiring constant polling. Polling would waste processor time checking devices repeatedly. Interrupts improve efficiency by allowing the system to respond only when devices request service. Direct memory access improves performance for large data transfers. Instead of sending data through the processor, direct memory access controllers transfer data directly between devices and memory. This frees the processor for other tasks. Direct memory access is common in storage controllers, network cards, and high-speed input and output devices. The operating system coordinates direct memory access by setting up transfer requests and handling completion signals. Input and output scheduling helps manage competition for devices. Storage drives often receive multiple read and write requests. The operating system schedules these requests to reduce movement on mechanical drives or to balance wear on solid-state drives. Network interfaces manage queues of packets for sending and receiving. Printers handle multiple jobs through a spooler, which stores documents until the printer is ready. Scheduling policies aim to maximize throughput while maintaining fairness. File systems interact closely with input and output systems. When an application reads a file, the request travels through several layers. The file system interprets the path, locates metadata, determines block addresses, and sends requests to the storage driver. The driver translates requests for the device. The device retrieves data and sends it back through the same layers. This chain of communication must handle errors, permissions, and timing issues. Input and output systems rely heavily on caching. Caches store frequently accessed data in memory. When the system reads a block from storage, it saves it in the cache. If the application requests the same block again, the system reads it from memory rather than from storage. This reduces delay and reduces wear on the device. The operating system manages caches by deciding when to keep, remove, or write back cached data. Cache policies influence performance and consistency. Hot swapping allows devices to be added or removed while the system is running. Operating systems detect new devices, load drivers, and configure settings automatically. This feature is common for storage devices, network interfaces, and external peripherals. Hot swapping requires careful coordination to avoid data loss. The operating system must ensure that pending operations complete before removing devices. Error handling is critical for input and output systems. Devices may fail, lose power, or send corrupted data. The operating system monitors devices and responds to errors. It may retry operations, switch to backup devices, or inform the user. File systems and network protocols include error detection and correction mechanisms. Checksums help detect corruption. Redundant arrays of storage can recover from failures. Network protocols retransmit lost packets. Reliable error handling protects data and maintains smooth operation. Input and output systems support asynchronous communication. Asynchronous operations allow programs to continue running while waiting for data. For example, a program can request a file and receive a signal when the data arrives. This improves responsiveness, especially for applications that handle many small requests. Asynchronous systems rely on callbacks, promises, or event loops to process results. The operating system coordinates asynchronous operations by tracking pending requests and delivering notifications. Device virtualization expands the flexibility of input and output systems. Virtual machines emulate devices so that guest systems believe they are interacting with real hardware. Hypervisors route requests between virtual machines and physical devices. Containers rely on virtual file systems and network namespaces. Virtualization requires careful input and output management to provide isolation and performance. The operating system and hypervisor cooperate to handle these tasks. Modern input and output systems support a wide range of hardware. Mobile devices rely on sensors such as accelerometers, gyroscopes, and location hardware. Servers rely on fast network interfaces and high-capacity storage systems. Consumer devices include cameras, displays, audio systems, and gaming controllers. The operating system provides consistent interfaces so applications can work across many types of hardware. This abstraction allows developers to create programs without worrying about specific devices. Understanding input and output systems reveals how operating systems communicate with the environment. These systems manage devices, handle data transfer, coordinate timing, and maintain reliability. Later chapters will examine scheduling algorithms, system calls, security mechanisms, and access control. Each topic depends on the input and output systems that support communication across the entire computer. Chapter 9: Scheduling Algorithms and Fair Distribution of CPU. Time scheduling determines which process or thread runs at any moment. Because modern systems often run many tasks at once, the operating system must decide how to divide processor time among them. This decision affects responsiveness, fairness, efficiency, and power consumption. Scheduling is fundamental to operating system design because every program depends on receiving time on the processor. This chapter explains how scheduling works, how algorithms differ, and how operating systems balance competing demands for CPU resources. A scheduler manages the ready queue, which contains processes and threads that are prepared to run. Each entry in the ready queue includes the state, priority, and necessary information to resume execution. When the processor becomes available, the scheduler selects the next thread according to its algorithm. The scheduler must switch context, restore register values, and update the program counter. These actions must occur quickly so that switching does not slow the system. The simplest scheduling algorithm is first come, first served. Processes run in the order they arrive. This approach is easy to implement but does not perform well in interactive environments. Long-running tasks can delay shorter tasks, causing slow response times. First come, first served works better for batch systems than for desktops or mobile devices. Another basic strategy is shortest job first. The scheduler selects the task that requires the least processing time. This minimizes average waiting time but requires the system to estimate job length. Estimation may not be accurate. Shortest job first favors short tasks and can delay long tasks for extended periods. Round-robin scheduling is widely used for interactive systems. Each task receives a small time slice. When the time slice ends, the scheduler moves the task to the end of the queue and selects the next one. Round-robin provides fair distribution of CPU time. The system selects time slice lengths carefully to balance responsiveness and overhead. Short time slices improve responsiveness but increase context switching. Longer time slices reduce overhead but may cause slow interactions. Priority scheduling allows some tasks to run before others. Each process receives a priority level. The scheduler selects the highest priority task whenever possible. This approach suits systems with real-time requirements or critical tasks. However, priority scheduling can cause starvation if low-priority tasks never receive time. Operating systems often include priority aging, which gradually increases the priority of tasks that wait for long periods. This prevents starvation and maintains fairness. Multi-level queue scheduling divides tasks into categories such as interactive, batch, or real-time. Each category has its own queue and scheduling policy. The scheduler selects tasks from high-priority queues before lower ones. This structure suits systems where different types of workloads coexist. Multi-level feedback queues extend this idea by allowing tasks to move between queues based on behavior. Tasks that use too much CPU time may move to lower priority queues. Interactive tasks benefit from higher priority queues. Real-time systems require deterministic scheduling. These systems must complete tasks within specific time limits. Hard real-time systems cannot tolerate missed deadlines. Soft real-time systems enforce deadlines but allow occasional delays. Real-time schedulers often use rate monotonic or earliest deadline first algorithms. These algorithms assign priority based on task frequency or deadline. Real-time scheduling ensures that critical tasks meet timing requirements but restricts flexibility for general workloads. Modern operating systems combine multiple scheduling strategies. Desktop systems aim for responsiveness because users expect immediate reactions from applications. Servers aim for throughput and balanced performance across many requests. Mobile systems must optimize power consumption by reducing unnecessary activity. Cloud platforms schedule tasks across virtual machines and containers. Each environment influences scheduling policies. Multi-core processors complicate scheduling because the scheduler must decide not only which task runs, but also where it runs. Some threads benefit from staying on the same core because caches contain useful data. This concept is called processor affinity. Schedulers try to keep related tasks on the same core to improve performance. However, they also must balance load across all cores. Operating systems use sophisticated algorithms to track core usage, temperature, and workload distribution. Interactive tasks need special care. Graphical applications, user interfaces, and input handlers require low latency. If the scheduler delays these tasks, the system feels slow. Many operating systems monitor user activity and adjust scheduling decisions during active use. They prioritize tasks that manage input, windows, and real-time interaction. This makes the system feel smooth even when background tasks are running. Background tasks include indexing, updates, backups, and maintenance. The scheduler assigns lower priority to these tasks so they do not disturb foreground activity. When the system becomes idle, background tasks can run more aggressively. This balance helps maintain performance while completing necessary work. Virtualization adds another layer to scheduling. Hypervisors schedule virtual CPUs on physical CPUs. Guest operating systems schedule processes inside virtual machines. Coordination between these layers requires careful design. Hypervisors must allocate time fairly among virtual machines. They also must provide predictable performance for guests. Scheduling becomes even more complex when containers share resources across many services. Energy-efficient scheduling has become important for mobile and embedded devices. Schedulers reduce power consumption by consolidating workloads, allowing cores to enter low-power states. They also adjust frequency and voltage based on demand. Energy-aware scheduling must consider thermal limits, battery life, and user expectations. Operating systems combine hardware power management features with scheduling strategies that reduce unnecessary work. Correct scheduling improves security as well. Some attacks rely on precise timing or resource starvation. Schedulers that randomize time slices or enforce strict fairness reduce the risk of timing-based attacks. Isolation between tasks prevents interference. Secure scheduling ensures that malicious tasks cannot prevent critical tasks from running. Understanding scheduling reveals how operating systems keep systems responsive and balanced. Scheduling ensures fair distribution of processor time, supports interactive applications, manages real-time requirements, balances workloads, and promotes stability. Later chapters will explore system calls, security mechanisms, access control, virtualization, and mobile systems. Each of these topics relies on effective scheduling to provide reliable operation. Chapter 10, System Calls and the Interface. Between applications and the kernel, system calls form the bridge between applications and the operating system kernel. Applications cannot access hardware directly. They cannot read storage devices, modify memory outside their own space, or control processors without permission. The kernel enforces protection and manages resources, so applications must request services through carefully controlled mechanisms. System calls provide this controlled path. They allow programs to perform tasks while maintaining safety, security, and consistency. This chapter explains how system calls work, why they are essential, and how operating systems organize communication between user space and kernel space. Programs run in user space, which is a restricted area of memory designed to prevent accidental or harmful actions. The kernel operates in a privileged mode with full access to hardware and system resources. Because of this separation, user space programs must ask the kernel to perform actions on their behalf. System calls allow these requests to occur safely. A system call begins when a program executes a specific instruction that changes the processor mode from user space to kernel space. This transition is controlled and logged to prevent misuse. System calls support many operations. They allow programs to open files, read data, write data, allocate memory, create processes, communicate through sockets, and interact with devices. Each system call corresponds to a specific service provided by the kernel. When a program needs to read a file, it issues a system call that passes the file descriptor and buffer address to the kernel. The kernel validates permissions, locates the file, retrieves data, and returns results to the program. System calls create a safe and predictable interface for all these operations. To manage system calls effectively, operating systems use tables that map call numbers to kernel functions. When a program triggers a system call, the processor consults the system call table to find the correct kernel routine. This process is efficient because system call numbers are fixed and standardized. Different operating systems use different system call sets. Linux, for example, provides a wide range of calls for file operations, memory management, process control, and inter-process communication. Windows uses a layered approach where system calls interact with subsystems before reaching the kernel. System calls must handle errors gracefully. If a program attempts an operation without proper permissions, the kernel returns an error code. If a file does not exist, a specific code indicates the missing resource. If memory cannot be allocated, the kernel notifies the program. Error codes help developers understand why operations fail and allow programs to respond appropriately. Proper error handling increases stability and user satisfaction. System call performance is an important concern. Switching between user space and kernel space takes time, so excessive system calls can slow applications. Modern operating systems use optimized pathways to reduce overhead. Some systems use fast system call mechanisms that rely on special processor instructions. Others use caching and buffering to reduce the number of calls required. Developers design applications to minimize system calls for performance-critical tasks. Security is one of the strongest reasons for using system calls. The kernel validates every request, it checks permissions, verifies memory addresses, and ensures that operations follow rules. System calls enforce boundaries between processes. They prevent unauthorized access to files, devices, and memory. This protective layer is essential for maintaining system integrity. Without system calls, programs could bypass controls and compromise the system. System calls support inter-process communication. Programs may need to send messages, share memory, or synchronize actions. System calls provide safe methods for establishing connections, creating shared regions, and sending signals. These mechanisms allow cooperation between programs without risking corruption or exposure of sensitive data. The kernel manages communication by controlling permissions and enforcing isolation. System calls play an important role in process management. When a program starts a new process, it issues a system call to request creation. The kernel prepares memory, initializes structures, and assigns identifiers. When a program ends, it issues a system call to terminate. The kernel reclaims memory, closes files, and updates records. Without system calls, process creation and termination would not be possible. System calls also support waiting for processes, retrieving status, and sending signals to control behavior. System calls relate closely to file systems. Reading and writing files require system calls. Creating directories, removing files, changing permissions, and renaming entries all depend on system calls. These operations must be validated, logged, and performed consistently. The kernel uses file descriptors to track open files. System calls manipulate these descriptors and maintain accurate records. This structure supports safety, reliability, and performance. System calls interact with input and output systems. Writing to the screen, reading keyboard input, sending network packets, and receiving data all require system calls. These actions require coordination between drivers, buffers, and device controllers. The kernel ensures that communication occurs smoothly. It prevents interference between tasks and ensures that each device receives commands in the correct order. Virtual memory systems also rely on system calls. When a program requests more memory, it uses a system call. When it maps files into memory, it uses system calls. When it changes protection on pages, the kernel performs the adjustments. Virtual memory adds flexibility by allowing programs to expand beyond physical limits. System calls support this flexibility while enforcing safety. System call design varies across operating systems. Unix and Linux systems use simple, well-defined calls that follow clear patterns. Windows uses a layered model with additional subsystems. Mac OS combines Unix-style calls with its own frameworks. Each approach reflects design priorities such as performance, compatibility, or ease of use. Understanding these differences helps explain how applications run on different platforms. System calls form the foundation of communication between programs and the kernel. They support file systems, memory management, scheduling, security, networking, and device interaction. They enforce boundaries and prevent unauthorized actions. They create consistency across applications and hardware. Later chapters will explore security mechanisms, access control, virtualization, and distributed systems. Each topic depends on safe and efficient system call behavior. Chapter 11, Security Mechanisms. Inside operating systems. Security forms one of the strongest responsibilities of any operating system. Systems must protect memory, files, devices, and resources from unauthorized access. They must prevent harmful actions, isolate processes, detect threats, and preserve stability. Security mechanisms operate quietly beneath the surface, ensuring that programs behave safely and that data remains protected. This chapter explores the internal structures that provide security, the strategies used to defend systems, and the role of the operating system in enforcing boundaries. Security begins with separation between user space and kernel space. User space programs run with limited privileges. They cannot directly control hardware or access memory outside their assigned region. The kernel operates in a privileged mode, where it manages processes, memory, devices, and system calls. This separation prevents programs from disrupting the system. If a program attempts an unsafe action, the kernel blocks it. This architectural design forms the foundation of modern security. Access control extends this separation by assigning permissions to files, processes, and devices. Each file has an owner and permission bits that determine who may read, write, or execute it. Groups allow controlled sharing among multiple users. Other permissions restrict access for everyone else. Linux and Unix systems use user, group, and other permissions. Windows uses access control lists that specify rules for individual accounts and groups. Mac OS combines these approaches. Access control prevents unauthorized reading or modification of data. Authentication confirms identity. Operating systems verify users when they log in by checking passwords, keys, or biometric data. Passwords are stored in hashed form, so they cannot be read directly. Strong authentication mechanisms prevent unauthorized access. Some systems use two-factor authentication to increase security. Authentication logs track attempts, successes, and failures. These logs help detect suspicious activity. Authorization determines what authenticated users may do. Even after identity is confirmed, users must follow permission rules. Authorization controls access to files, devices, network resources, and system services. For example, administrative actions require elevated privileges. Operating systems separate regular users from administrative users to reduce risk. This principle of least privilege ensures that actions match the user role. Process isolation prevents one process from interacting with another without permission. Each process receives its own address space. Memory protection prevents processes from reading or writing outside this space. System calls enforce interaction rules. If a process needs to communicate with another process, it must use approved channels such as message queues, pipes, or sockets. Isolation contains errors and faults. If one process crashes, it does not affect others. The kernel monitors system calls to enforce security. Every system call request includes arguments, memory addresses, and identifiers. The kernel validates each request. It checks whether the process has permission to perform the operation. It checks whether memory addresses are valid. It checks whether file descriptors correspond to open resources. If anything appears unsafe, the kernel denies the request. This gatekeeping ensures consistent behavior and prevents harmful actions. Integrity protection prevents unauthorized modification of system files, settings, and kernel components. Some operating systems use mandatory integrity systems that restrict changes to protected files. Mac OS includes system integrity protection. Linux supports mechanisms such as extended attributes and integrity checking through security modules. Windows includes features that protect critical parts of the operating system. These protections prevent tampering by malware or unauthorized users. Security modules add additional layers. Linux supports modules such as SE-Linux and AppArmor. These modules enforce rules that control how processes interact with files, devices, and other processes. Linux uses a policy-based system that labels resources and defines permitted interactions. AppArmor uses profile-based restrictions that define allowed operations. These modules provide fine-grained control and help protect systems from exploitation. Memory safety is essential for security. Techniques such as stack protection address space layout randomization, and executable space protection reduce the risk of attacks. Stack protection detects corrupted return addresses. Address space layout randomization places memory regions in unpredictable locations. Executable space protection prevents data from being executed as code. Together, these features make it more difficult for attackers to exploit vulnerabilities. The kernel also manages secure communication. Socket operations, encryption libraries, and certificate handling rely on system support. Operating systems provide random number generation for cryptography. They manage key storage and enforce secure communication protocols. Network stacks include protections such as packet filtering and validation. These features ensure that data sent and received across networks remains safe. Audit logs record activity. Logs note login attempts, permission changes, system errors, and unusual events. Administrators review logs to detect threats or diagnose issues. Some systems include real-time monitoring tools that alert administrators when suspicious activity occurs. Logging supports accountability and helps identify problems before they cause harm. Sandboxing provides controlled environments where programs run with restricted privileges. Browsers use sandboxes to isolate web content. Mobile operating systems use sandboxes for applications. Sandboxing limits access to files, memory, and system services. Even if a sandboxed program encounters malicious content, the damage remains contained. Sandboxing relies on process isolation, system calls, and permission systems. Kernel hardening techniques make the operating system more resilient. These techniques include reducing attack surfaces, removing unnecessary components, and enforcing strict validation rules. Hardened kernels disable features that are rarely used but may introduce risk. They enforce stronger protections for memory and system calls. Hardening reduces the chances that vulnerabilities can be exploited. Updates are a crucial part of security. Operating systems receive regular patches that fix vulnerabilities. The kernel, system libraries, drivers, and applications all require maintenance. Automated update mechanisms help ensure that users receive security improvements promptly. Delayed updates increase exposure to known vulnerabilities. Modern systems also include security tailored for virtualization and cloud computing. Virtual machines require strict isolation from one another. Hypervisors enforce boundaries and ensure safe resource sharing. Containers depend on namespaces and control groups for isolation. Cloud platforms use encryption, identity management, and monitoring to protect distributed systems. These environments extend security mechanisms beyond individual machines to large-scale infrastructure. Security mechanisms ensure that the operating system maintains integrity, protects data, and enforces safe behavior. They support authentication, authorization, isolation, logging, and monitoring. They adapt to different environments and respond to evolving threats. Later chapters will examine user permissions, virtualization, mobile operating systems, and distributed systems. Each of these topics builds on the internal security foundations that protect modern computing. Chapter 12, User Accounts, Permissions, and Access Control Models. User accounts and permissions define how people and processes interact with an operating system. They determine who may read files, modify settings, run programs, or access devices. These controls preserve privacy, protect data, and prevent harmful actions. Modern operating systems rely on detailed access control models that specify rights for individuals, groups, and system components. This chapter explains how accounts work, how permissions operate, and how access control creates safe and organized environments. A user account represents an identity within the operating system. Each account has a unique identifier, which the system uses to track ownership of files and resources. When a user logs in, the operating system verifies identity through passwords, keys, or other authentication methods. After authentication succeeds, the system assigns a session linked to that identity. All actions during that session follow the permissions associated with the account. Operating systems support multiple account types. Regular user accounts have limited privileges. They may run programs, access personal files, and use basic system services. Administrative accounts have elevated privileges. They may install software, change system settings, manage users, and modify protected files. Guest accounts offer temporary limited access. Separating account types helps maintain security. Most users do not require full control, and reducing privileges limits potential harm. Permissions determine what each account may do. In Unix and Linux systems, permissions are divided into 3 categories: user, group, and other. Each category receives read, write, and execute bits. Read allows viewing file contents. Write allows modification. Execute allows running a program or entering a directory. This simple structure supports flexible control. For example, a user may own a file, share it with a group, and restrict access for everyone else. Windows systems use access control lists instead of permission bits. An access control list contains entries for users and groups. Each entry specifies allowed or denied actions, such as reading, writing, deleting, or modifying attributes. Access control lists offer fine-grained control in suit environments with many users and complex requirements. macOS uses a combination of Unix permissions and access control lists, providing both simplicity and precision. Group accounts help manage access for multiple users. A group contains several user accounts. Permissions assigned to the group apply to all members. This simplifies administration. Instead of modifying permissions for each user individually, administrators assign permissions to groups. Examples include staff, administrators, and developers. Group-based access supports organized workplaces and educational environments. Authentication verifies that users are who they claim to be. Passwords remain common because they are easy to implement. Passwords must be stored securely using hashing techniques to prevent exposure. Some systems use key-based authentication, biometrics, or smart cards. Two-factor authentication increases security by requiring 2 forms of verification. Authentication logs record attempts and help detect unusual activity. Authorization follows authentication. Once identity is confirmed, the operating system checks whether the user is allowed to perform the requested action. Authorization rules apply to files, processes, devices, and network resources. These rules ensure that even authenticated users cannot perform actions beyond their intended role. Authorization helps implement the principle of least privilege, which limits users to the minimum rights required. Ownership plays a central role in permissions. The account that creates a file becomes its owner. Owners may modify permissions or transfer ownership. In multi-user environments, ownership helps track responsibility and protects personal data. Operating systems enforce ownership rules strictly to preserve security. Role-based access control organizes permissions around roles rather than individuals. A role defines a set of responsibilities. Users assigned to a role inherit its permissions. This model works well in organizations where tasks align with job functions. Examples include finance, support, and system administration. Role-based models simplify management and reduce errors. Mandatory access control enforces system-wide rules that users cannot change. In this model, resources receive labels and security policies define allowed interactions. Linux supports mandatory access control through modules such as SE-Linux and AppArmor. Mandatory access control provides strong isolation and prevents unauthorized communication between processes. It is useful in government, research, and enterprise environments that require strict security. Discretionary access control allows users to modify permissions on their own resources. Owners decide who may access their files. Unix and Linux systems rely heavily on discretionary access control. While flexible, this model requires users to understand permissions to avoid accidental exposure. Discretionary models work well in personal and shared environments where collaboration is common. Access control extends beyond files. Processes, devices, sockets, and system resources also require protection. Operating systems track permissions for each type of object. For example, device files represent hardware interfaces. Only authorized users may access these files. Network ports require permissions to prevent unauthorized listening or connection attempts. Process controls limit signals and debugging actions to safe interactions. Session management controls how users interact with the system. Sessions begin when users log in and end when they log out. During a session, the system tracks active processes, environment variables, and access rights. Sessions enforce boundaries and prevent unauthorized persistence. If a user ends a session, processes associated with that session terminate unless specifically designed to continue. Audit logs record access attempts, permission changes, authentication events, and administrative actions. Logs help administrators monitor the system and detect suspicious behavior. Regular review of logs identifies patterns that may indicate misuse. Logging supports accountability and helps maintain trust in the system. Modern systems support account integration across networks. Directory services such as Active Directory, LDAP, and identity management platforms centralize account control. Users sign in once and access resources across many systems. Centralized management simplifies permissions and improves consistency. Network-based authentication and authorization require secure communication and careful configuration. Operating systems continue to evolve access control models. As computing shifts toward cloud environments, identity becomes distributed. Users authenticate through remote services. Permissions apply across virtual machines, containers, and applications. Cloud platforms use token-based systems to handle identity and authorization. These systems integrate with traditional operating system controls to maintain security. Understanding user accounts, permissions, and access control helps explain how operating systems protect resources. These mechanisms preserve privacy, limit harm, and support safe collaboration. Later chapters will explore virtualization, mobile systems, and distributed environments. Each topic builds on the access control principles described here. Chapter 13, Virtualization and how operating systems run inside other systems. Virtualization changes the way computers use hardware. Instead of running one operating system directly on physical components, virtualization allows multiple systems to share the same hardware. Each system behaves as if it has its own processor, memory, storage, and devices. Virtualization increases flexibility, improves resource use, and simplifies management. Modern servers, cloud platforms, and development environments depend on it. This chapter explains how virtualization works, how virtual machines operate, and how operating systems adapt to running inside other systems. A virtual machine is a software representation of a physical computer. It includes virtual hardware such as processors, memory, storage controllers, and network interfaces. The operating system inside a virtual machine cannot distinguish virtual hardware from physical hardware. It follows the same procedures for memory management, process control, and file systems. This illusion is created by a layer of software called a hypervisor. Hypervisors come in two major types. Type 1 hypervisors run directly on physical hardware. They manage virtual machines and assign resources. These hypervisors suit servers and large-scale environments because they offer strong performance and isolation. Type 2 hypervisors run inside a host operating system. They rely on the host to manage devices and memory. These hypervisors suit personal use and development because they are easy to install and manage. Both types provide the same essential function of creating and supporting virtual machines. The hypervisor controls how resources are allocated. It divides processor cores among virtual machines. It assigns portions of memory. It provides virtual storage and virtual network interfaces. Each virtual machine receives a share of the physical resources. Scheduling decisions determine when each virtual processor runs. Memory mapping techniques allow multiple virtual machines to share memory efficiently. Storage devices may be shared or may use virtual disks that behave as files on the host system. Virtualization depends on hardware support. Modern processors include features that allow virtual machines to run efficiently. These features reduce the overhead of switching between virtual machines and simplify memory management. Hardware-assisted virtualization allows the hypervisor to trap sensitive operations and emulate them safely. Without hardware support, virtualization would be slower and less reliable. Memory virtualization is an important component. Each virtual machine uses its own page tables. The hypervisor must translate virtual machine addresses into physical addresses. Some systems use nested page tables, where one table maps guest addresses to intermediate addresses and another maps those addresses to physical memory. This method allows the guest operating system to manage its own mapping without interfering with the host. Memory virtualization protects isolation and prevents virtual machines from accessing each other. Storage virtualization uses virtual disk files. These files behave like physical disks from the perspective of the virtual machine. The guest operating system partitions, formats, and writes to the virtual disk just as it would with real hardware. The hypervisor manages the file and translates operations into commands for the physical storage device. Some virtual machines use shared storage areas, which simplify migration and backup. Network virtualization creates virtual network interfaces inside each virtual machine. These interfaces connect to virtual switches managed by the hypervisor. Virtual switches route traffic between virtual machines and physical networks. Network virtualization allows complex topologies to exist entirely in software. This supports testing, development, and cloud networking. It also allows isolation between virtual environments. Snapshots provide a powerful feature in virtualization. A snapshot records the state of a virtual machine at a moment in time. This includes memory, storage, and device states. Users can return to the snapshot if needed. Snapshots simplify testing and improve reliability. They also support backups and recovery. However, snapshots consume storage space and must be managed carefully. Virtualization improves efficiency by allowing multiple systems to run on one physical machine. Servers typically underuse resources when running a single operating system. Virtualization aggregates workloads and increases utilization. This reduces hardware costs and power consumption. It also simplifies maintenance because virtual machines can be moved between physical hosts without interruption. This capability, called live migration, supports maintenance and load balancing. Isolation is a major advantage of virtualization. Each virtual machine operates independently. Problems in one machine do not affect others. This isolation supports security. If a virtual machine becomes compromised, the hypervisor prevents the attack from spreading. Hypervisors enforce strict boundaries and ensure that resources remain separate. This isolation also allows developers to test software in safe environments. Containers provide another form of virtualization. Instead of virtualizing hardware, containers virtualize the operating system. Each container runs applications in isolated environments using shared kernel resources. Containers start quickly and consume fewer resources than virtual machines. They suit cloud platforms and scalable services. Operating systems provide namespaces, control groups, and file system features to support containers. Containers rely on operating system features rather than hypervisors, making them lightweight and efficient. Virtualization changes how operating systems handle scheduling, memory, and input and output. A virtual machine schedule depends on the hypervisor schedule. Memory allocation depends on hypervisor decisions. Input and output operations pass through virtualized devices. Operating systems must handle timing differences, virtual interrupt behavior, and shared resource environments. Modern systems include optimizations for virtualization. Para-virtualized drivers improve performance by allowing the guest operating system to communicate directly with the hypervisor. Cloud computing relies heavily on virtualization. Cloud providers run thousands of virtual machines and containers across large clusters. The hypervisor or container engine allocates resources dynamically. Customers request virtual machines, and the cloud platform provides them instantly. Virtualization supports elasticity, where resources expand or contract based on demand. It also supports multi-tenancy, where multiple customers share hardware safely. Security within virtualized environments requires careful design. The hypervisor becomes a target because it controls many systems. Strong isolation prevents virtual machines from escaping their boundaries. Administrators must protect management interfaces, monitor resource usage, and secure communication channels. Containers require additional controls to prevent interference between workloads. Understanding virtualization explains how operating systems adapt to shared environments. Virtual machines behave as if they run on dedicated hardware. Containers behave as if they run in isolated operating system instances. Hypervisors and container engines manage resource allocation, scheduling, and communication. Later chapters will explore mobile operating systems, distributed systems, and future design trends. These topics build on concepts established by virtualization and resource sharing. Chapter 14: Mobile and Embedded Operating System Design. Mobile and embedded operating systems differ from desktop and server systems in important ways. They must operate reliably under limited resources, support specialized hardware, conserve power, and provide safe and predictable behavior. Many modern devices rely on mobile and embedded systems, including smartphones, tablets, home appliances, sensors, industrial controllers, and automotive systems. This chapter explores how these systems work, how they differ from traditional operating systems, and how they balance efficiency with functionality. Mobile operating systems support smartphones and tablets. These devices rely on touchscreens, wireless communication, cameras, sensors, and battery power. Mobile systems must provide smooth interfaces, responsive applications, and secure environments while conserving energy. Because battery life is limited, mobile operating systems adjust scheduling, memory use, and input and output strategies to reduce power consumption. They optimize background activity and restrict heavy processing when devices are idle. Android and iOS are the two dominant mobile operating systems. Android is based on a Linux kernel and uses a modular structure. Applications run in isolated environments using managed code and sandboxed permissions. Android supports a wide range of hardware and manufacturers. This flexibility makes it highly adaptable, but also requires strong compatibility management. iOS is built on a Unix-based foundation and integrates tightly with Apple hardware. Its consistent environment simplifies optimization and security. Both systems include strong application sandboxes that limit access to files, sensors, and networks. Touch interaction shapes mobile operating system design. User interfaces must respond instantly to gestures such as swiping, tapping, and pinching. Mobile systems use optimized graphics pipelines to render smooth animations. They prioritize tasks that manage input and display. Background processes receive lower priority to ensure that the interface remains fluid. Mobile kernels support advanced scheduling strategies and memory management tuned for short bursts of activity. Security plays a central role in mobile systems. Applications run with limited permissions. They must request access to sensitive data such as cameras, microphones, location, and contacts. The operating system enforces these permissions and informs users when applications request them. Mobile systems isolate applications using sandboxes that prevent direct interaction between them. This protects user data and limits the effects of malware. Regular updates and centralized application stores help maintain security. Embedded operating systems support devices that perform specific tasks. These systems appear in home appliances, medical equipment, automotive controllers, and industrial machines. Embedded systems often have strict timing requirements. They must respond to events quickly and predictably. Real-time operating systems provide determinism by guaranteeing that tasks complete within specific timeframes. They use real-time schedulers, predictable memory allocation, and fast interrupt handling. Determinism remains more important than throughput in these environments. Embedded devices operate under tight constraints. They may have limited memory, slow processors, or restricted storage. Embedded operating systems must minimize overhead to fit within these limitations. They may eliminate features such as graphical interfaces, multitasking, or complex networking. Some embedded systems run a single task repeatedly. Others support multiple tasks, but restrict scheduling to predictable patterns. Designers must balance functionality with constraints. Many embedded operating systems use modular kernels. The kernel includes only essential components, and additional features load as needed. This approach reduces memory use and improves reliability. Some embedded systems use microkernels, where services such as device drivers run in user space. Microkernels improve fault isolation because failures affect fewer components. However, microkernels require efficient communication to avoid performance penalties. Power management is essential for both mobile and embedded systems. Mobile devices rely on batteries, and embedded systems often run on limited power sources. Operating systems control power states for processors, memory, and peripherals. They turn off components when idle and adjust clock speeds to balance performance and energy use. Sensors and wireless radios consume significant power, so systems manage them carefully. Applications must follow guidelines to avoid draining power. Storage in mobile and embedded systems differs from traditional environments. Devices often use flash memory. Flash memory wears out over time, so operating systems use wear leveling strategies to distribute writes. File systems for flash devices use structures that minimize block erasure and support efficient access. Examples include F2FS for mobile systems and specialized file systems for embedded devices. Storage reliability is critical because many embedded devices handle important tasks. Networking also differs in these environments. Mobile systems rely on wireless communication, including cellular networks, Wi-Fi, Bluetooth, and near-field communication. Operating systems manage wireless scanning, signal transitions, roaming, and power consumption. Embedded systems may use wired protocols such as CAN in automotive networks or industrial field bus standards. These protocols prioritize reliability, low latency, and predictable timing. Applications in mobile and embedded systems face restrictions. Mobile systems limit background execution to preserve battery life. Applications may run only during user interaction or under specific conditions. Embedded systems may load applications at boot and run them continuously. Updates must be reliable because failures can affect safety or functionality. Some embedded devices require remote updates for maintenance. Secure update mechanisms ensure that only trusted code runs on the device. Hardware integration is a significant part of mobile and embedded operating system design. Sensors such as accelerometers, gyroscopes, GPS receivers, and light detectors provide context for mobile applications. Embedded devices may include specialized hardware for control systems, signal processing, or communication. The operating system must include drivers for these components and manage them efficiently. High-quality integration improves performance and reliability. As technology advances, mobile and embedded operating systems support more complex applications. Smartphones now perform tasks once reserved for desktops. Embedded devices increasingly participate in networks and support remote monitoring. These developments require stronger security, improved resource management, and advanced scheduling techniques. They also require operating systems to handle large numbers of software components while preserving stability. Understanding mobile and embedded systems helps explain how operating systems adapt to specialized environments. These systems support devices with unique constraints, strong security needs, and precise timing requirements. They use tailored kernels, scheduling strategies, power management techniques, and storage solutions. The next chapter explores distributed systems and operating system support for cloud environments, where resources span many machines and services. Chapter 15, Distributed Systems and Operating System. Support for the cloud. Distributed systems extend computing beyond a single machine. Instead of relying on one system to process data and run applications, distributed systems use many interconnected computers that work together. These systems share tasks, replicate data, and coordinate behavior across local networks, data centers, and global cloud infrastructures. Modern operating systems include features that support distributed environments by managing communication, synchronization, resource allocation, security, and reliability across multiple machines. This chapter explores how distributed systems work, why they matter, and how operating systems support them. A distributed system appears to users as a single system, even though it consists of many machines. These machines may run different operating systems, use different hardware, or perform different roles. The operating system must support communication between nodes, manage network resources, and maintain consistent behavior. Distributed systems help overcome limitations of single machines. They provide scalability by adding more nodes. They provide reliability through redundancy. They support large workloads by distributing tasks. Communication is central to distributed systems. Nodes exchange messages using protocols that ensure delivery, order, and integrity. Remote procedure calls allow programs to request services from other machines. Distributed file systems allow nodes to share data. Network sockets support direct communication between processes across systems. The operating system manages these channels by providing network stacks, buffering strategies, and error handling. Reliable communication remains essential for coordination and performance. Synchronization ensures that distributed nodes cooperate correctly. Because nodes run independently and communicate with delays, timing becomes uncertain. Distributed systems use logical clocks, vector clocks, and algorithms that detect conflicts. For example, if two nodes update the same data independently, the system must detect the conflict and resolve it. Synchronization mechanisms help maintain consistency, especially in environments where data is shared across multiple locations. Distributed file systems allow nodes to access files stored on remote machines. These systems use caching, replication, and version control to maintain performance and reliability. Examples include NFS for local networks and cloud-based file services. Distributed file systems must handle failures gracefully. If one node becomes unavailable, others must continue functioning. Replication ensures that data remains accessible even when failures occur. The operating system coordinates these features by managing storage drivers, network communication, and caching policies. Cloud environments rely heavily on distributed systems. Cloud platforms run applications across clusters of virtual machines and containers. The operating system supports these environments through virtualization, resource control, and networking. Virtual machines allow different operating systems to run on the same host. Containers allow lightweight application isolation. Operating systems use namespaces, control groups, and virtual network bridges to support containers. These features allow cloud platforms to scale services automatically based on demand. Resource allocation across distributed systems requires careful planning. Nodes may have different capabilities. The operating system tracks available memory, processor usage, storage capacity, and network bandwidth. Load balancers distribute tasks among nodes to improve performance and prevent overload. Resource scheduling must consider latency, geographic distribution, and failure patterns. Distributed environments also require strong security to prevent unauthorized access across networks. Fault tolerance forms a major goal of distributed systems. Machines fail, networks disconnect, and processes crash. Distributed systems include redundancy and recovery mechanisms. Replication stores multiple copies of data. Heartbeat messages detect failures. Consensus algorithms allow nodes to agree on actions, even when some nodes are offline. The operating system supports these features by managing communication and persistent storage, ensuring that recovery can occur after failures. Distributed databases rely on operating system support for network communication, storage management, and synchronization. These databases spread data across multiple nodes to improve performance and availability. They must ensure consistency and handle conflicts. Some systems prioritize strong consistency, while others prioritize availability or partition tolerance. The operating system provides reliable foundations for these trade-offs by ensuring that storage and communication remain stable. Security in distributed systems requires strong encryption, authentication, and access control. Nodes communicate across networks that may not be secure. Operating systems provide tools for secure sockets, key storage, and certificate validation. Authentication services confirm identities. Authorization rules control access to resources across nodes. Logging and auditing remain essential for tracking distributed interactions. Containers have become central to distributed computing. They run microservices, which represent small, independent components of larger applications. Operating systems support microservices through container engines that manage isolation, networking, and resource control. Orchestration systems, such as Kubernetes, coordinate containers across clusters. They handle scheduling, scaling, and service discovery. The operating system provides namespaces, C groups, and networking features that orchestration systems depend on. Distributed systems also rely on clock synchronization. Although clocks on different machines drift over time, distributed systems require agreement on timing for logging, ordering events, and coordinating tasks. Time services use algorithms that estimate delays and adjust clocks. While perfect synchronization is impossible, operating systems support time protocols that keep nodes close enough for practical purposes. Edge computing extends distributed systems to devices near the user. Instead of sending all data to central servers, some processing occurs on local devices. This reduces latency and improves performance. Edge devices rely on lightweight operating systems that support networking, security, and resource management. They coordinate with cloud systems to share data and distribute workloads. Understanding distributed systems helps explain how modern computing scales across global infrastructure. Operating systems support communication, synchronization, resource management, security, and recovery. They enable virtual machines, containers, microservices, and cloud platforms. These features allow applications to run across many machines while appearing unified and reliable. The next and final chapter explores long-term trends that shape the future of operating systems as technology evolves. Chapter 16, The Future of Operating Systems and Long-Term Design Trends. Operating systems continue to evolve as technology changes. The foundations remain the same. They manage processes, memory, security, storage, networking, and communication. Yet the environment around them grows more complex. Devices shrink, cloud platforms expand, artificial intelligence spreads, and computing becomes more distributed. These changes influence long-term design trends in operating systems. This chapter explores how operating systems may develop in the coming years, how new challenges will shape them, and how current concepts form the base for future innovation. One major trend is deeper integration with cloud environments. Cloud computing already influences operating system design. Many applications run across clusters rather than single machines. Systems must coordinate containers, virtual machines, and microservices. Operating systems increasingly provide features that simplify integration with cloud platforms. These features include improved virtualization, stronger identity systems, and enhanced support for distributed communication. As cloud usage grows, operating systems may become more cloud-aware, adjusting resource management and scheduling to align with remote services. Artificial intelligence and machine learning also influence operating systems. Many devices now include specialized processors for neural networks. Operating systems must support these processors with drivers, libraries, and scheduling rules. They must manage workloads that increasingly depend on model inference and data processing. Some operating systems may integrate machine learning into resource management, predicting usage patterns and adjusting behavior. Machine learning may help optimize scheduling, power management, and security analysis. Security remains a dominant concern. Threats evolve quickly as attackers find new vulnerabilities. Operating systems must strengthen isolation, restrict access, and improve integrity protection. Stronger sandboxing, advanced encryption, and hardware-based security features will become more common. Operating systems may adopt more mandatory access control models and deeper verification of software components. Automated detection of anomalies will help identify unusual behavior. Security mechanisms will continue expanding to protect cloud services, mobile devices, and connected systems. Energy efficiency becomes more important as devices rely on batteries or operate in large data centers. Operating systems will adopt improved scheduling strategies that reduce power usage. They will manage hardware components more aggressively by turning off unnecessary features. They will coordinate with processors that adjust frequency and voltage dynamically. Energy awareness will extend to distributed environments where systems balance workloads to reduce energy consumption across clusters. Quantum computing introduces new possibilities and challenges. Although quantum computers remain specialized and rare, operating systems may eventually support hybrid environments where classical and quantum systems cooperate. This requires new abstractions for processes, memory, and scheduling. Quantum systems behave differently from classical systems, and operating systems must adapt. Early research explores how to manage quantum tasks and integrate them with existing platforms. Edge computing continues to expand. Devices closer to users handle tasks such as data processing, caching, and machine learning. These devices require lightweight, efficient operating systems. They must handle intermittent connectivity, local processing, and secure communication with cloud services. Edge systems may rely on specialized kernels designed for minimal latency. They may include modules for sensor fusion, local inference, and privacy protection. Operating systems must scale from powerful servers to tiny embedded devices while maintaining consistent behavior. User interfaces evolve alongside hardware. Voice control, gesture recognition, augmented reality, and virtual reality require operating systems to support new types of input and output. Systems must process complex data streams from cameras and sensors. They must schedule tasks that handle rendering, tracking, and interaction. These workloads require tight control of timing and resource allocation. Operating systems will adapt their models of input, display pipelines, and responsiveness. Storage trends also influence future design. Non-volatile memory technologies continue to improve. These technologies combine the speed of memory with the persistence of storage. Operating systems must adapt file systems, caching strategies, and memory managers to take advantage of new storage. They may blend memory and storage into unified spaces. This requires new models for data persistence and protection. Virtualization and containerization will remain central. Operating systems will improve isolation and performance for containers. They will support multi-tenant environments where many customers share hardware. Containers will become more lightweight and more secure. Hypervisors will become more efficient. Systems may combine containers and virtual machines to gain benefits from both models. Orchestration tools will become more tightly integrated with operating systems. Network communication will shape future systems. Faster wireless networks, satellite communication, and fiber infrastructure require improved networking stacks. Operating systems must handle higher bandwidth, lower latency, and more devices. They must support advanced protocols, adaptive routing, and secure communication channels. As the number of connected devices increases, operating systems must handle congestion, address limits, and security challenges. Privacy will influence future operating systems. Users expect more control over their data. Operating systems must support fine-grained permission systems. They must provide clear indicators of data access. They must restrict background collection and enforce transparency. Privacy rules will shape how applications access cameras, microphones, location services, and personal data. Operating systems will support encrypted storage and secure containers to protect sensitive information. Future operating systems may become more modular. Instead of large monolithic systems, they may include components that load as needed. Modular designs allow systems to run on devices with different capabilities. They also improve security by reducing the number of active components. Microkernel designs may become more popular as devices require strong isolation and reliability. Modular systems may adapt more easily to changes in hardware and workload. Automation will play a larger role in system management. Operating systems will monitor performance, detect problems, and adjust behavior automatically. They may restart services, redistribute loads, or change configurations without user intervention. Automated tuning will improve performance and reduce the need for manual management. These capabilities will suit cloud environments where thousands of systems operate together. Understanding future trends helps explain how operating systems evolve from current designs. The core principles remain stable. Operating systems manage resources, enforce boundaries, support communication, and provide environments for applications. New technologies create new demands, and operating systems respond with new features, security models, and resource strategies. The operating system continues to serve as the foundation of computing, adapting to changes in hardware, networks, and user expectations.